Hi, I am Professor Andy Gunawardena, and today we are going to discuss gradient descent. Gradient descent is a powerful optimization technique guiding algorithms to learn by finding the best solution. Imagine standing atop a hill, aiming to reach the lowest point in a valley, taking steps based on the slope beneath you. Each step leads you closer to minimizing error, following the path to the optimal solution. This is the essence of gradient descent, a step-by-step approach that directs us towards the best possible outcome. So how should we think of gradient descent? Mathematically speaking, we have a loss function with respect to theta. We guess some value of theta to begin with, and then adjust it moving towards the minimal loss, or what we call the optimal theta that minimizes loss. This requires developing methods to find these theta values. We note that univariate view only shows one theta, but in practice we have to look at many thetas based on how many independent variables we choose. In the bivariate view, or trying to find two thetas, it is like going towards the bottom of a volcano without knowing which direction you are going. So here is how we think of gradient descent. It is an iterative method. We start with some theta 0 and then calculate theta 1 based on a formula given. The formula takes theta 0 and then subtract the gradient or derivative of the loss function with respect to theta to find the theta 1. We make an important observation here. If the gradient of the loss function is positive, as shown, the theta 1 is closer to optimal than theta 0 as we approach the optimal value from right. On the other hand, if gradient is negative, that is, theta 0 is selected from the left of the optimal, then theta 1 is obtained by subtracting the negative gradient or adding gradient that makes the theta 1 larger than theta 0, which is closer to optimal from the left. Hence, the same formula works, even if we guess initial theta from left or right. In both cases, we approach the optimal value. That is the beauty of this formula. But there is a problem of using the equation we discussed so far. If the gradient is too high, then it is possible that we might subtract too much from theta 0 to get theta 1, and it can overshoot the optimal point. For example, if the optimal theta is 2, and we start with theta 0 equals 3, and then gradient is 1.5 at that point, then theta 1 will be 3 minus 1.5, and we have gone to the left of optimal theta. That is not good. On the other hand, if the gradient is too low, then convergence might be too slow. This allows us to introduce a learning rate alpha that we can control. If we do not see much convergence because it overshoots, we can make alpha small. Or if we see slow convergence is too slow or error is going down slow, then we can increase alpha. As in all machine learning, these hyperparameters like alpha are important to control the convergence process. It is all hard work. So, we show how to find the derivatives from the loss function using calculus. You can also refer to your calculus notes if you have forgotten how to take partial derivatives. We can then define the iterative formulas for theta 0 and theta 1. One note of caution. When doing implementation, it is critical to update thetas simultaneously, and we will see that in the demo. Now, let's see how this might work with a real example. Here we try to find the best fit regression line for a real dataset. The dataset is high temperature, x-axis, and peak demand, y-axis. When we plot, it does seem like a line fit might be a good idea, so we can find a linear regression line. This is also a simplistic model that tries to predict the demand based on just one variable temperature. Obviously, in practice, this is too simplistic, and we need more than one independent variable temperature to predict demand, but this is good enough for our demo purposes. Before we implement this, which you will see later, we need to normalize data as temperature and demand, as they can come from two scales. Using a min-max normalizer, we can map all values to be between 0 and 1. Let's see how the iteration works. We will start with theta 0 and theta 1 both equals to 0. In iteration 1, we can see that the error is large, like 1427, and we cannot see a regression line anywhere close. However, now we iterate and find theta 0 and theta 1 new values, and the error has gone down to 292, and we see a glimpse of a regression line appearing from lower right. So far, so good. As we do third and fourth iterations, we see that the error continues to go down and regression line appears to come for a good fitting. Iterations 5 through 10 continues to reduce the error, and we're reaching a good regression line shown in green. After many iterations, we can decide that the error has reduced enough, and we take the best fitted line. In the next video, we will see an actual implementation of gradient descent. We also note that gradient descent is not limited to regression problems. It's a versatile optimization algorithm used across various types of machine learning models. Bye until next time.